Welcome everyone, my name is Mark Salai from the Budapest University of Technology and Economics, and in the next few minutes I'm going to present our paper called AnnaBellaDB Key Value Store Made Cloud Native. This is a joint work of the HSL Lab Research Group and the Ericsson Research Hungary. Nowadays, cloud native paradigm has become a widely used concept with the goal of ensuring the elasticity and reliability of our applications running in the cloud. We have plenty platform choices to run our code in the cloud, like the OpenStack, Kubernetes, or for instance Amazon Lambda. But we can generally consider that the applications consist of multiple components. They can be distributed across many servers in the cloud or edge infrastructure, and also they can use shared data between each other. If we use a cloud management system like a Kubernetes, it handles the orchestration, scaling, and other lifecycle events of the deployed application containers. However, these kind of platforms are tailored for stateless applications only. But what happens if we'd like to use stateful apps? One possible solution if we use a distributed key value store like Redis for this purpose. In such systems, typically a hash function decides where to store, in which server, the state. Unfortunately, this may result in inter-server communication, that is additional network delay in the response time of the application. In our short paper, we propose a new state storage method, a state layer, which is a latency and access pattern aware storage layer over the server cluster with the goal of minimizing the access time of the externalized state or data of the applications. In our paper, the state layer actually a distributed memory store where all servers have a part. All components include access pattern monitors, and it has a master component which maintains the network latency, the list of the stored states, and also it can be optimized the locations of the data to minimize the delay. For example, if the app1 initially has created a state, but during the time app2 accesses it more time, then the access pattern monitor indicates this, and the master component can optimize the location of the data. So in summary, the three key elements of the proposed state layer are the state placement, the access pattern monitor, and the state locality optimization. In our paper, we present a possible implementation of such kind of state layer. We have extended an open source solution called Anna to create our proof of concept, what we named as AnnaBellaDB. We made our code available on GitHub. We made some synthetic measurements highlighting the advantages of our state layer over the legacy hash function-based solutions. Since our prototype is based on Anna, which uses a hash function, we consider its performance as a proper basis for comparison. We emulated two types of cluster topologies in terms of network latency. One, geographically distributed edge cloud network called InterDC, and a data center network named as IntraDC. We made measurements on single server where the hosts run in separated containers. In our first measurement, we used applications which read 10 times and write 1 time a certain state from and to the state layer. The x-axis of the figure depicts the time in the seconds passed during the measurement, while the y-axis shows the average of all access times of all applications in a 2 seconds wide sliding window. The red line represents the Anna access time, and the green one is the result of AnnaBellaDB. The dashed vertical lines show the moments when a new application has been launched. For example, in the first phase, the first application was deployed to server 1. In this case, the placement module of AnnaBellaDB decided to save a state locally in server 1, contrary to Anna, who stored it in server 2, resulting in longer access time. In the second phase, the two solutions more or less operated similarly. However, within this time, the data is stored in server 2. In case of AnnaBellaDB, thanks to the continuously monitoring, the data was migrated for server 1, resulting in a spike in the access time after the third application deployment. After the fifth application has launched, our solution migrated the data to server 3, from where the majority of the access originated, resulting in lower average access time of the applications. We also examined how the proposed state layer behaves in the intra-DC environment, so we repeated the evaluation that we have seen in the previous slides, but for now, the preliminary network delay was configured for 300 microseconds. According to our results, we found that there is no considerable difference in the two databases' performance since the low intra-DC network delays are comparable to the processing latency of the server. However, due to the fact that AnnaBellaDB is optimized to efficiently handle the dynamics of applications, we also examined the corner case when an application is continuously moving from one host to another. In this scenario, the application was initially deployed to server 1 and migrated forward every minute to server 2, server 3, and so on. We used the same application as before. Anna stored the data in server 2 during the measurement, while AnnaBellaDB initially saved it into server 1 and migrated it to the appropriate host in every occasion when the application was migrated. To conclude, in the case of AnnaBellaDB, the application always has the opportunity after it was migrated to access the state locally. To conclude our work, we show that AnnaBellaDB can achieve more efficient state access time performance compared to the legacy ones in edge cloud systems due to the data placement optimization. In the future work, we plan to extend our measurements to create a comprehensive evaluation, and also we want to compare our AnnaBellaDB to key value stores using cache to identify the scenarios when the state layer could perform more efficiently. Thank you for your attention.